Okay, so going back to yesterday and the day before, if we want to get the rate of reaction, you got the change in concentration of a reactant over the change in time. That's what we did the first day. That was the potable. All right. Or from yesterday, for a first order reaction, we have K times the concentration of A. And notice A has an exponent of 1 that you can't see because it's first order. Those are the things that we've already learned. The units for this would be seconds to the negative first. How do you feel? Okay, cool. Now the deal is, remember I showed y'all this a second ago. If I draw a line or a graph of concentration of A versus seconds or time, it's going to look like that. But if you integrate it with calculus, you can get a straight line for a first order if you, instead of plotting just the concentration of A, if you plot the natural log of the concentration of A, you will get a straight line if you do the natural log. That's all that is, okay? That's all the you don't need to know calculus, but I'm just trying to explain to you like what happened. Now the deal is, if you remember with zero order, K, the slope of the line is equal to the rate. Well, the slope of this line is K. That's why today we're going to talk about these integrated rate laws. I got to just skip that part of your book because it's like, I don't understand. So, the natural log of a first order, that yields it so that K is still the slope of the line, right? When this is the thing, when this is a graph, that's not a straight line. You know what I'm saying? So that's why. That's why we're doing the natural log, so that we get a pretty straight line, and then K is equal to the slope of that pretty straight line. How you feel? You all right? All right, so on the way in the door, you got an M&M. We talked about how zero order concentration versus time is a straight line. Now, what letter does, I'm going to put this back. What letter, I feel like I drew something on the board. It went away. Oh, there we go. What letter does an L look like? Oh, excuse me, what number does an L look like? So that's how you remember it. The natural log of concentration being a straight line, if you have graphs to choose from, and the natural log of concentration versus time is a straight line, then you know it's first order. Do you understand? We're going to get into that. But that's how you keep it straight. Because the most common kind of question for this is not these crazy math things, which do come up especially on the, this isn't funny anymore. There. They do come up on the free response, but on the multiple choice, they're going to give you a bunch of graphs. One's going to have like concentration versus time in straight line, but oh, zero order. Natural log versus time, straight line, first order. So that's easy, right? That I like those kind of questions. Maybe you won't be able to do the math like everybody else. I hope you can, but you can remember that. Anyway, oh, this little formula right here is on your formula sheet. So they're real stingy with the kinetics formulas, but let's take a look at them, okay? I want you to find where they are on here, so when you're taking your test, whatever, you can easily see where we are. All right, now, so this is the formula, the natural log of A, and this just means at some time, minus the natural log of the concentration of A, and this 0 means at 0 seconds or initially, is equal to the negative value of K times T. So, anyway, that's that. All right, now, y'all know that in math class, y equals mx plus b is a straight line, right? And I just told you that this makes a straight line. I just told you that. So, this is what's on your formula sheet, right? Y'all know how it's mx plus b? If you want to make a slope-intercept of this, think about it like this. You want mx plus b. So, if I move this to the other side, plus b, that makes a plus. If I move the other one to the other side, it ends up being minus. You see what I'm saying? That's how you can remember. Now, talk to your group, okay? What does b even mean in y equals mx plus b? Talk to your neighbors. What does that b mean? Flashbacks to 6th grade. Okay, so throw back to being 12 years old. B means what, Amanda? Yeah, and so look here. This, remember, is our y-axis. I'm just making sure no child's left behind today. The natural log of a at this point intersects with the y-axis. So anyway, when you rearrange it, the reason that it ends up on this side is because that is the y-intercept. The natural log of a at this point is the y-intercept. So that's your slope, and that's your y-intercept. So that's another way you can remember how to rearrange it. Yes. Yes. But not everybody can make that mental leap. So I'm making sure no child's left behind today. There you go, everybody. What did you say?
I said I feel like I'm normally the one left behind, but I got that far.
Good. Well, I'm just making sure. The thing is, though, on your formula sheet, if you're asked to interpret a graph and you have that y-intercept, this formula sheet doesn't say anything about that, and it doesn't have it rearranged like this. So you have to know that that's the one that needs to go to the other side, and that's fine. All right, so moving on. So again, y-intercept is the natural log of a at the beginning, and then the slope is negative k. So that rate constant has to be positive. We had talked about that a little bit, and so you do see the decrease in the slope there. So it's got negative k, and if you look at the formula, it's negative kt. All right, so how does this even apply to anything? Well, let's look. If I'm asked to write the rate law for this reaction, I can see that it only has one reactant, and I can tell what is the order of the reaction. 1. And the reason I can tell without anything else, I can't tell by looking at this, by the way. I can tell by looking at this, because the natural log of the concentration over time is a straight line. So I can tell it's first order. So I know it's first order. So the rate law is rate equals K, and then my only reactant is A. And that's it. That's the rate law. Done. That's the easy part. What? If it's a straight line of concentration versus time of zero. But you see how it's a natural log of the concentration? So if it was zero order, it would be that. Okay? Good question. So that's the rate law. We can do that, right? Yay! So now we're going to solve for K. Now, if I go back and draw that again, do I have the rate? Do I have my rate here? No. Do I have K? No. So I don't have either one of these. There's a couple different ways to do this, but I like to just use the formula. So I can't just substitute stuff into here. I'm going to have to use math. I am going to have to solve for K, I'm actually going to use this formula. And so what we're going to do, the natural log of all this stuff, that is A sub 0, y'all. And A at some other time, we can pick any of these. And I'm just going to pick this one. I'm sorry about that. I'm going to pick the second one, which is at 50 seconds, it looks like. So let's go ahead and do that. I have this data on a little paper here because I don't want to have to flip back and forth. But I'm going to go to my little white screen, and I'm going to use the formula I just told you about, and I'm going to solve for K, okay? So here we go. I'm going to write the formula down, and then I'm going to rearrange it. So I have the natural log of A, and then, what was it, 50 seconds? So A sub 50. Don't let that freak you out. This is just a way of labeling things. I'm just labeling that. I'm not going to do math with that. I'm just saying the concentration of A at 50 seconds. I'm just labeling it, okay? And then that's going to be, we're going to subtract, the natural log of A at the beginning is equal to negative K. And I'm solving for K. So I'm going to divide both sides by negative T. How do you feel about algebra? Hope you feel good about it. How does that math make you feel? Do you understand what I did? So, if I solve for K, K is going to be equal to, need to make sure I don't write my own shadow, the natural log of A at 50 seconds. Well, the concentration of A at 50 seconds was 0.012. My pen is just, I can't do anything with it. I have another one. Let me borrow this pen. I don't know. I feel like that's not a good idea. Actually, I know it's not. That won't do good things for us. I'll just have to be really careful. Sorry. Is something going on next to it? Oh, it's this kid's every day during lunch. Okay, so what was it? 0.017? Yeah. Oops, brackets. There we go. And then subtract the natural log at the beginning, the natural log at the concentration at the beginning. And then this t, y'all, is this t. It's the same t. So the time is 50 seconds. And all of this, again, is negative. That's making me sad. So now you're just going to use your calculator, and you're going to solve for k, and that'll be our rate constant. You have to use a lot of parentheses with this, okay? So be careful. Part of today's lesson is going to be you learning how to use your calculator. And then the units for k, because it's first order, is seconds to the -1, and it works out because you can see here it's seconds to the -1 because it's on the bottom of the fraction. Did everybody get this number in their calculator? If you didn't, we have a problem. We need to talk about it. So that's also 3.3 times 10 to the -3rd. I mean, yeah. This reminded you of to the notation test. Yes. Sure. Okay, so you have to put your number in first. Alright, did everybody get it? Don't need help anybody with their calculator. Oh, good? Alright, we're not done. That was B. The answer to B is 3.3 times 10 to the -3rd. Now, we have to now solve for the concentration of A at 500 seconds. So, what I'm going to do to solve for the concentration of A at 50 seconds, or 500 seconds, excuse me. Do y'all see on the, can you see in your PowerPoint? We're doing part C now. So what I'm going to do is I'm going to go back to the formula, and now I'm going to rearrange it such that the natural log of A at 500 seconds, and again, I'm just labeling this. This is just a label. And I'm going to go ahead and rearrange the formula, which is just going to equal negative KT, and then plus the natural log of A at the beginning. Okay, so I'm going to fill in what I have now. Natural log of A at 500, that's what I'm solving for. I'm sorry? That's a negative KT. Is equal to negative K. K was what we just figured out. 3.3 times 10 to the -3rd. And then the seconds is 500 seconds. Then I'm going to add the natural log of A at the beginning, or initially. The concentration of A initially was 0.020 molar. Now, in my calculator, if you're not good at calculators, negative 3.3, and then the EE button, I'll give you this, 10 to the whatever, and then times 500. I would kind of hit equals every time. This part should give you negative 1.65, okay? Then I'm going to add parentheses, the negative, the natural log of 2O, close parentheses twice, and you end up getting now. Make sure you get negative 5.56 in your calculator, okay? Everybody got it? I'm solving for the concentration as in a molarity of a reactant at 500 seconds. Does it make sense that my answer would be negative 5.56? And am I done? Like, is my answer, this is what I really want. Like, I want this gone, and I want this to equal that. I'm not done. Y'all remember in math class how you make a natural log go away? What's the kind of that inverse operation of that? Yeah, so if I raise both sides, check this out, whatever you do and stop. If I raise this side, or e to the power of this side, and e to the power of this side, you know, you can do the same thing to both sides as long as you do both sides, right? So that makes the natural log go away. And now I'm left with a concentration of A at 500 seconds is equal to e raised to the power of negative 5.56. So in my calculator, I'm going to say e to the, notice how e and natural log are the same button. There's a reason for that. And I find that the concentration of A at 500 seconds, ooh, I gotta be careful with my pen. Okay, sorry about that. It's equal to, all that is equal to, it looks like 3.8 times 10 to the third, negative third. And you could say molar, or you could put it in brackets. Sorry about my crazy pen. How are you feeling about that? No good? The only time you're going to have to worry with that E button is if you're solving for concentration, because it's going to be the natural log of it. You're going to have to make that natural log go away. Most of the time on these, you won't have to, like if you're solving for K, you won't have to use the E button. It's only if you're solving for one of these concentrations. All right? Are you okay? Well, that's just one way. That's one of them. Oh, this is why my friends cried today. Moving on. So we did all that, and I want to show you how they did it. It's worth talking about real quick. The rate law, I mean, that it is what it is. It's first order because the graph is a straight line, and it has, you know, just one as an exponent. What they did here, that's the same thing we did, right? We solved for K the same way. They didn't break it down into steps, but it's the same stuff. They do use a different method here for half-life. That's what I was thinking of. All right, talk to your friends about this question. It's not math, it's concept-based. And so I'm going to pick somebody, and I want you to tell me what's going to happen to the slope of this line. Remember that when we integrate these integrated rate laws, when we go to plot them, plot the data, the slope of the line is K. Right, so the steeper the slope, the bigger the slope, the faster the reaction is going to happen. This still goes back to yesterday, y'all. Look, the bigger the K, the bigger the rate. So higher temperatures speed up reactions, right? Lower temperatures slow them down. So rate, if it's colder, K is going to be small. You understand? So, and that's good. This is K. This line is K. Right? It's negative K, but still the slope, that whole thing is same principle. No, y'all saw it. Are you okay, Grace?
Yeah, I was
Okay. We're not done. It's not to the part you cried yet. Sorry. I wish it wasn't like this. Does that make it better? I'm not enjoying myself either.
Some teachers enjoy it.
You're on video. Behind. So at a lower temperature, what's going to happen to the slope or the kind of shape of this graph? Victoria, what'd you get? So if I think about it having a steeper slope, what that means is it's like a steeper hill, really, right? That means that the reaction is the reaction rate constant is going to look like this, which would mean that the reaction would go faster. Does that make sense if you have a lower temperature? No. So when we're thinking about slopes of lines, like a zero slope is a horizontal line now. Y'all know that, right? So if I actually lower the temperature, it is going to decrease the slope of the line because the slope of the line is K, and K is going to be smaller when I slow down the reaction. Am I saying things that I feel like I'm playing a fun little pop-up game? Oh, I don't like this game. There we go. I need to stop minimizing that. So, okay. I can't do anything about it. I need to bum a pen off a teacher that doesn't use these, which I think there's a lot of those people. Let me use my mouse. I know that works. So anyway, the slope of the line ends up being less, like I said, and that's your new line, the natural log of A, because your K is going to be less, which slows down your rate because K times all that stuff is the rate. How you feel? This still goes back to yesterday. Okay, so half-life for first order reactions. That's the time it takes for the concentration of the reactant to decrease by half. Yes, on your homework, there's a couple easy, like 8th grade problems where it's like, you start with 10 crayons. The half-life's 20 seconds. How much remains after 60 seconds? And that's 3 half-lives, so it would be 2.5 crayons. Have you done that kind of question before? Yeah, you're going to have to do that. That's your homework. That's part of it. That's not really on this test, but what it is on this test is first order reactions have a constant half-life. The other ones don't. Okay? So how that applies to us is, if you look on your formula sheet, the half-life for a reaction that is first order is it's 0.693 divided by K. And so if you can solve for K using the integrated rate law with the natural logs, right? Then you can put K into this formula and get the half-life in seconds. How does that make you feel? Okay. There's a harder way to do it, so I'm all about that. All right, so let's look at this. What is the order of this reaction, everybody? First order, because the natural log of concentration over time is a straight line. So anyway, now y'all be careful when you're doing your homework, and be careful right now. These graphs, in the calculator, when you plug in the natural log of the concentration, the answer is negative 3.91. You don't need to go natural log of negative 3.91. It is already that. Do you understand what I'm saying? This is not the concentration at 0 seconds. That don't make any sense. This is the natural log of the concentration at 0 seconds. They already did the math. You don't need to plug that in your calculator. You follow? So same thing here at 600 seconds. The natural log of the concentration at 600 seconds is negative 4.93. So this is actually easier, right? This is good. This is good. So we want to find the half-life. So what we're going to have to do first is we're going to solve for K, and we're going to solve for K using this formula, the natural logs, and then we're going to take the K and we're going to 0.693 divided by, just like on here. Okay. So let's go ahead and do that. And I actually think that I can just work it out right here. So if you look at the formula sheet, I'm just going to substitute. Okay. So the natural log of A at some time, and we're going 600 seconds, is negative 4.93. Okay, and then subtract out the negative log of A at the beginning. So that's going to be minus 3.91. And that equals negative K times time. And what's the time? 600. And now you just push buttons in your calculator. Sounds like a sweet deal, right? So minus a negative is plus a positive. I have to get something. I have to do this. I can't do it. Maybe if I get a different battery. I don't think Mr. Harden has used his pens before, so I bet I can just. Mr. Harden, let me have something that looks like this. They're my plans here to make it happen. All right. So anyway, cross your fingers, children. Looks so far so good. Nope, just kidding. I'm so sad. I'm so sad. I don't like this game. Anyway, that's a plus, right? That was a plus sign. Plus. Here, I'll do it with my mouse. That looks good. So when you add negative 4.93 and 3.91, you get negative. I can't do this. Okay. Bad things are gonna happen now. So this way it is. Like another pen thing is probably gonna pop up, and this one isn't gonna work. But that's obviously not working. Okay, good. So I forgot what I was saying. It was a negative 1.02 is equal to, oh, it's working. Oh, wow, I'm so excited. Negative K and then times 600. So in that seconds, I'm going to divide both sides by 600 seconds. And so, I'm going to do it actually by 100. And so K is equal to a really small number. Negative 600.0017. Am I done? Like, did I do all the things yet? I have a solve for half-life? No, I have the rate constant. So now I can take this K, and if you look on your formula sheet, 0.693 divided by K, don't just start. You get 408. And that's seconds. And that's just sig figs. I have just 3 sig figs is what I did. Did y'all follow me here as I did this with these numbers? Were you okay here? Can you say that a little bit louder? So this is 3 sig figs, and this is only 1. And I mean, really, it would only be 1, but they're probably doing this as like an exact number, so it doesn't count anyway. Do you know what I mean? All right. So how do y'all feel now? You got that? It's on the formula sheet. So for this, and then again, one more time, that half-life on here, that T sub half, that's half-life in seconds. It only works for first order, so these magic numbers only first order, okay? Can't do that for second order too. Okay, moving on. I know, like, please stop this room. Make it stop. Make it stop. So we solved for K in the same way. What they did here, they, K, listen, the K is the slope. So we solve for K using the formula, which I like. Or you can do change in molarity over change in time. This was the first day's lesson. I like the formula better, whatever. It doesn't matter. It's the same thing either way. So there's your slope. Remember, K is the negative slope. So anyway, this is how we did it. Oh, no, this is not how we did it. This is, I don't know why they did this. You have a formula for it. If you want to just plug stuff in and like think about what would half of it be. I'm not into this. 0.693, okay? Yeah, let's do that. Divided by K. They don't have, I don't know why they didn't use that. All right, so there's a couple different ways to think about this mathematically and graphically. This question is asking which of the following processes has a shorter half-life. If you have a short half-life, that means like half would react, half of it would turn into product. If it was 10 seconds, that would be a fast reaction versus 10 years. That would be a long half-life, so think about that. But talk to your friends and figure out which one would have a shorter half-life, and then to justify means mathematically or graphically support your answer with an additional sentence. That's what that means when you're taking the AP exam. Okay? So, anyway, talk to your friends, figure one out, and I'll call somebody in a second. Okay. Okay, so which one one would have a shorter half-life and why? I need a justification. Ken. Okay. The formula? Okay, so if you're taking the AP exam and you wanted to use the formula as your justification, you'd have to do those math problems and show your work and say that, you know, when you use the half-life equation for first-order reactions, blah, blah, blah. Or there's other ways you can do it. Does somebody else do a different way? Anybody? Grace? No? Y'all used to use the formula? Well, another way to think about it would be that K is equal to the slope of the line. So the slope of the line would be greater for reaction 1, which would mean that the reaction rate would also be greater for reaction 1, so that would yield a shorter half-life. So either one of those would be fine. Anyway, okay, so today we have talked about zero-order reactions, molarity versus time, straight line. First-order reactions, natural log of concentration, because the L looks like a 1, is a straight line. Second-order reactions, you have a fraction, which is 1 divided by the concentration, is a straight line. How many numbers are in a fraction? 2. So second-order reactions, when you graph 1 over the concentration, you're writing 2 numbers. Second order makes a straight line. Okay. So again, still with the K being the slope. Now look, what's the difference on this part of the formula versus first order? What's the difference? This is not negative. Let me show you why. I know you want to know why, but I have to show you. Like, I won't be able to sleep tonight if I don't explain stuff. So this is still time in seconds, right? Good times. And then if I plot 1 over concentration here, let's just throw out some numbers and see what happens mathematically. Let's say our initial concentration is 10 molar, okay? Well, 1 divided by 10, well, that's 0.1, so at 0 seconds, 0.1, right? Well, what if the concentration of reactant is going to go down over time, right? Well, now what if it's 1 over 5? Well, that's, going to be 0.2. What? This is me explaining stuff. Now it's going to be 1, right? And then later on it's going to be, what if the molarity goes down to 0.1, right? So now the slope of the line is positive. I don't need a negative sign in front of it because you're taking 1 and you're dividing it by subsequently smaller numbers. So if you have a whole pie and you divide it out by 10 pieces and then 5 pieces and then 1 piece, then whatever. Those pieces get bigger. Those pieces get bigger. That's why. Yeah. Okay, so anyway, never seen this before. You know what? I'm not. I'm really not. But that's okay. I think my I am recording. Okay, so what has happened?
Pretty sure 15 minutes of the video.
You know what? It is what it is. All right, so that is when you do these kind of problems, you're gonna do them the same way we just did the first order reactions. But you gotta have enough sense to know that you gotta pick this equation. Does it say on that sheet which one's for first order, which one's for second order? Does it? No, it doesn't say any of that. So you have to remember what I told you about an L looking like a 1. Okay. But we're gonna solve for K or solve for anything. We're gonna plug stuff in and do it the same way. So this is not the worst thing that's ever happened to you. So just like we had talked about how if we rearrange the formula, this is the Y-intercept. I've never done these kinds of things with my pen before. I'm going to go back over to my computer now. So I'm doing the best I can. This is my Y-intercept, my B, because it's the concentration at the beginning. That's where you're going to start, at that Y-axis. How you feeling? So there you go. What's going to happen on the AP exam is they're going to throw up a little graph for you, and then 1 over the concentration will be a straight line. 1 or natural log of the concentration will be a curve, and then the molarity will be a curve, or I won't even have that on there really, to be honest with you. And then you'll be like, well, which order is it? And you'll have to know it second because the graph is a straight line with 1 over it, okay? All right, so on this one, we're going to find the rate law and the rate constant. How many reactants do we have? Looks like we have 1. And can you tell, this is what I was talking about. So this makes a straight line, this does not. That's how you know it's second order, okay? So since it only has 1 reactant, please work. Since it only has 1 reactant, I give up. Since it only has 1, okay, I guess a red pen is what we're rolling with today. No, I don't think the pen is even working. This is what I told you, like, if you, okay, I think I got it for a second. Rate, oh, it was almost working. Rate is equal to K, always to K, and then since it's second order, NO2 squared. For the love of all things holy, that 2 is not because of the coefficient. That'll have nothing to do with it, okay? Do not be that kid. It is a 2 here because it is second order. Do you understand? That doesn't seem like a big deal, but it is a big deal because with equilibrium, those coefficients are the exponents. Yay! Yes, okay? So I'm trying to help you. Please work, please work, please work. All right, so let's go ahead and cross our fingers and hope that I can make this work to explain this one to you. So let's go ahead and take this data, and we're going to just fill it into the formula like we did with first order, but it's just a different formula, okay? You got to know which one's which. So here we go. I already gave you the rate law. Now we're going to solve for the rate constant. And so we're going to use the same formula, which is 1 divided by the concentration of A at some time minus 1 divided by the concentration of A at the beginning is equal to positive KT. Be careful. So what we're going to do is we're going to just take the time at 0, and you can pick any of the points in the graph or in the chart. So the concentration of NO2 initially, was 0.070 molar. And do y'all want to pick 100 seconds? Is that okay? You can pick any of them. Okay. So the concentration of A, and I'm just picking 100 seconds. Okay. So there. At 100 seconds, the concentration of A is 0.015 molar, and that is equal to K. And I should have rearranged it already. I'm sorry. Divide both sides by T. Right. And T is 100 seconds. Made it pretty far without being ugly. So now you're just going to solve for K. And this is no natural logs or anything needed. So I'm going to use my calculator. And 1 divided by 0.015 equals minus parentheses 1 divided by 0.07 close parentheses divided by 100, and you get K is equal to 0.523. Yeah, 266. So K is it's almost funny, but it's not. Okay, so K is equal to point.
Just write it.
I'm making a movie, that's why. So it doesn't. K is equal to 0.524, which we're going to round to 0.52. Okay, that's the answer. I did the best I could. Sorry, children. Apologize. Y'all got that? So now we have to solve for the concentration at some other time. Is that what it was asking, or did it even have that part? Or are we done? We're done. I kind of want to just write it real quick. Point 5 2. Okay, I'm glad we're done. I'm gonna have to get a new pen before tomorrow. All right, so going back, let's look at that again better. And so there's the rate law, and then we fill the stuff in. And then this is the last line. So here's the data from experiment in which the concentration over time for a second order process, and we can tell it's a second order process because 1 over the concentration of the reactant is a straight line. Sketch a line that shows the appropriate result that would be expected if it was completed at a higher temperature. So talk to your friends, and then you get 30 minutes to do practice. Have you thought about your answer? That was quick. All right, Sarah, what would the slope of the line look like now? Right, because the temperature is higher. So that would make my rate constant higher, and the rate constant is the slope of the line. Okay. All right, so why don't we go ahead and I'm going to stop the video, and then